Hello everyone. Today's topic of discussion is emitter bias configuration, which is another very important topic from analog electronic circuit. In the previous class, we have learned about what is biasing, what is fixed bias configuration. After fixed bias configuration, the next topic is emitter bias configuration. In case of fixed bias configuration, we have few disadvantages which can be eliminated with the help of emitter bias configuration. So let us see. These are my contents: constructional difference with fixed bias configuration, calculation of base current, calculation of collector current, calculation of collector to emitter voltage, saturation value calculation, and how emitter bias circuit is better than fixed bias configuration. So these calculations we have already made in case of fixed bias configuration also in our previous lecture. Now this is the constructional difference between the fixed bias configuration and emitter bias configuration. You can see in this figure, in fixed bias configuration we have only two passive resistances RB and RC. But in case of emitter bias configuration, we have three resistances. One extra resistance RE is connected to the emitter terminal, which is not available in case of fixed bias configuration. So this is the only constructional difference between fixed bias and emitter bias. Now, as we learned in our previous lecture, in any common emitter circuit, we have two loops: the input loop, the base emitter loop, and the output loop, which is the collector to emitter loop. So let us apply the KVL in the input loop or base emitter loop for emitter bias configuration. Now, the first voltage is VCC plus VCC, then move around the loop. The drop will be across RB resistance, and the current is IB. So the drop will be IB/RB, then minus VBE drop, then minus I into RE equal to 0. Now as we know, the IE current is equal to beta plus 1 IB. Substituting the value of IB in this equation, we get VCC minus IB/RB minus VBE minus beta plus 1 IB into RE equal to 0. So in place of IE, I have put beta plus 1 IB. Now grouping terms will then provide the following: minus IB in the bracket RB plus beta plus 1 RE. I have taken IB common, plus VCC minus VBE, because I need to calculate the value of IB current. So I have taken IB common. Now multiplying throughout by minus 1, so that I get a positive equation in the left hand side. Now the IB current will be equal to VCC minus VBE by RB plus beta plus 1 RE. So in fixed bias configurations, the IB current equation was VCC minus VBE by RB only. But in case of emitter bias configuration, in the denominator one extra term is there, that is beta plus 1 RE. Now the base collector loop or the output loop. Now here the loop is like this. So let us start from the IERE. So plus IERE plus VCE plus ICRC negative VCC. As the loop direction is opposite, so all these drops are taken as positive and the VCC is negative. Now as we know, IE current is nearly equal to IC current, and grouping terms gives VCE minus VCC plus IC RC plus RE. So I have put IC in place of IE, and VCE will be equal to VCC minus IC RC plus RE. Now this is very important equation. In case of fixed bias configuration, which we have discussed in our previous lecture, the VCE equation was VCC minus ICRC. Now one additional term RE is available here. Now again one more thing, in fixed bias configuration the voltage at emitter point was 0 because there was no resistance connected at emitter terminal. But now in this configuration we have one RE resistance connected in emitter terminal, and the drop will be IE into RE. Now again we know VCE is equal to VC minus VE. So we can calculate VC voltage, which is equal to VCE plus VE. So this VC voltage is a single subscript voltage. Now VC can also be calculated from this equation VCC minus ICRC, which you can get from this equation, VC equation. Now we know VBE is equal to VB minus VE. So VB can be calculated as VBE plus VE. So in this way we have calculated two single subscript voltage, VC and VB, and IC as usual is beta times of IB. Now the next two calculations are saturation value of current and saturation value of voltage. So let us determine the saturation value of current and saturation value of voltage from the output equation. Now the output equation states that VCC minus IC RC plus RE minus VC equal to 0. So ICQ is equal to VCC minus VC by RC plus RE. And as we know from the previous discussion, the saturation value of current can be calculated by taking or by keeping VCE is equal to 0 volt. So putting VCE equal to 0 volt, we get VCC by RC plus RE. And the saturation value of current can be calculated by keeping VCE is equal to 0 volt, which is VCC by RC plus RE, which we have seen here. What is the saturation value of voltage? Keeping IC equal to 0 milliampere, we got the saturation value of voltage, which is VCC, which is similar to the fixed bias configuration also. Now the VI characteristics of emitter bias configuration. So this is Y axis or current axis, this one is X axis or voltage axis. This is the curve for IB current. The line joining IC set and VC set is our load line. IC set is VCC by RC plus RE and VCE set is VCC, and this is our quotient point or Q point, or you can say operating point. Now let us see how emitter bias configuration is better than fixed bias configuration. In case of fixed bias configuration, we have seen one disadvantage, and that disadvantage is its stability, which is very poor. Now let us see how emitter bias configuration provides better stability as compared to the fixed bias configuration. Now we know the input loop current or IB current equation is VCC minus VBE by RB plus beta plus 1 RE. Now taking beta plus 1 common from the denominator, so the equation will be IB is equal to VCC minus VBE divided by beta plus 1 in the bracket RB by beta plus 1 plus RE. We also know IC is equal to beta times of IB, and beta plus 1 is nearly equal to beta, and IC is equal to beta IB. So beta into IB is VCC minus VBE divided by beta plus 1 is replaced with beta RB by beta plus 1 plus RE. In the next step, we can cancel the beta from the numerator and denominator, and the equation will be VCC minus VBE by RB plus beta plus 1 plus RE. Now this is our final equation. Now in this equations, if we will be able to make RB by beta plus 1 is very nearly equal to 0, or you can say very less than 1 or very small, then RB by beta plus 1 term can be neglected. Once this term is neglected, the above equation can be written as IC is equal to VCC minus VB by RE, and this current equation is completely independent of beta. So we need to keep in mind this equation, because this is a very important equation. Now from the previous equation we have seen that IC current is independent of beta, and as we know beta is temperature dependent, so any variation in temperature may change the value of beta, definitely, as we have seen in fixed bias configuration. Now output current depends on beta from this equation, because IC is equal to beta times of IB plus ICEO, and circuit current can be made beta independent by the use of emitter bias configuration, or by keeping RB by beta plus 1 nearly equal to 0. Now due to which operating point, or you can say quotient point, or you can say Q point, remain stable. So if due to any reason the beta changes, if beta changes in the circuit, then IC will not change. if IC will not change, the Q point will not shift towards either towards the saturation level or towards the cutoff level. So this is why emitter bias configuration is mostly used in case of many designs, many amplifier designs. So this is all about emitter bias configurations. So we have discussed everything about emitter bias configuration, how it is stable, how it provides stability to an amplifier circuit. So in the next lecture we will discuss about voltage divider bias configurations and how the emitter stabilization, RE stabilization will function in case of voltage divider configuration also. Thank you.